So today's lecture, we will start a new chapter, which is chapter 4, Sequential Circuits. Last lecture, or previous lectures on the first half of the course was about combinational logic circuits, which is there is no time dependence, no feedback, no memory, no storage elements. But here in sequential circuits, there is a memory element, or there is something related to the time, or there is a feedback. So in the previous examples, we used to do to make some programs, like to take the measurements from the sensors and do a certain action. But right now here, we need to have some time. And sometimes it can be as timers, sometimes can be as counters. So as timers, for example, when you make a traffic light, so when you make a program for it, so you will see like you need to wait a specific time for green, for red, and so on, and you need to have some measurements about how's like the traffic jam, if there is a lot of traffic or heavy traffic or not. Then there will be some like other complicated things in addition to the time. Counters, like the regular counter, when you count, build like a counters, or any other, like there are some other applications for that. So we need to have a memory element, and that memory to store data. That stored data can be as real-time timers, or it can be as, again, as counters, which is I will determine will the update will happen. So that update for the real time, we need to add something called clock, so it will make the real time change happens. So in the earlier in this course, or the first half, was combinational circuits. Now we will use the same techniques on the combinational. We keep using Carnot maps, keep using Boolean algebra, the other stuff, but we need to add memory elements. So we need to have some storage. That storage can be used as a feedback. So we see that there is a feedback going from the storage to be used. Therefore, the outputs will not only depending on the present inputs, but the outputs will depend on the present and past inputs. So outputs will depend on present and past inputs, and also it might depend also on past outputs. Like what? For example, the traffic light, the past output was red, then the next one will go to green. Then if it's green, then we'll go to yellow or orange, then it will go to red, and so on. So we need to have, sometimes the output, as I said, will be depending on present and past inputs, and will depend on also on the past outputs. So to see how the next state will be. So the overall, before discussing the sequential circuits, we need to know the how to create a memory elements. So that will be like maybe this week's, maybe next week lecture, which is how to create a memory elements from the devices that we have from the logic gates. So there are two types of sequential circuits. There is the synchronous, which is, as I mentioned, real time, or there is asynchronous, which we will determine what will happen depending on our turn or our choose. So the real time, it most likely will be connected to something called like a clocked or synchronous, which there will be like a clocked and like tick tock. So whenever there is tick tock, there will be a change. While asynchronous, which is I will determine, I will press this, or it will be not like regular as tick tock. So there will be a certain pattern that we assume to make the updates. So the synchronous, there will be, of course, in order to make it synchronous, there will be a clock generator. And that generator will create a periodic pulses. Again, imagine like the old watch, like wall watch, tick tock, tick tock. So each tick tock will create something called pulse, like this tick tock, tick, tock, and so on. Or you can imagine like tick is up, tock is down, tick up, tock is down, and so on. So it will create a pulse, and that pulse is called periodic. And the word periodic means it repeated itself, every a certain period of time. For example, when you look at the wall watch, tick tock, every 1 second it will repeat itself. Then for the pulse generator or clock generator, we have the choice. We can make it every 1 second, every half second, and so on. But it must be periodic, which means like the distance between tick and tock are exactly, or the time, the period, is exactly the same between what will happen after 1 hour, after 2 hours. So it will be, these pulses will continue forever with the same width, same period. No matter if I draw it different width, that's my handwritten, but it must be periodic. Okay? Then we have we need to create some storage elements. That storage elements, it can be separated into two types. There's types called latch, there's another one called flip-flops. So each one has its own characteristics. Then that's what we expect to see in the future flip-flops and latches, or like the future following classes, which is flip-flops, latches, which is those are basically storage elements that we can use to create a certain thing. Most likely, as we know, the logic gates are based on transistors, like NAND gates, NOR gates, and NOT gates. So we have three types. Then we can create AND, OR from all of these three gates, as we know earlier. So we know all of this based on CMOS or NMOS, PMOS transistors. So these transistors, we can create the logic gates. Then using these logic gates, we can create latches and flip-flops. After creating the latches and flip-flops, latches or flip-flops will be associated with 1 bit. Then the group to create 1 byte, for example, we need 8 latches or 8 flip-flops. This one example for making, we call it, as I said, like to create 1 byte or to store 1 byte. This 1 byte or this group of flip-flops or group of latches is called register. Then we can create a register which is associated with each byte. Each byte, or maybe 2 bytes, can be in 1 register, depending on the several factors. So we can create registers to store some bytes, which is larger number of bits. After that, we can create multiple registers to create the memory. So we can store the data based on this, like store the data into the memory. The memory will move it to the register. Then the register will move it to the flip-flops. The flip-flops will move it to the gates. Gates will move it to the transistors. Then it will be stored. Now, our next topic is how we can store the data into a small flip-flop or into a small latch or flip-flop. How can we create actually the flip-flop to store the data? So if we know how to do the basics, then the rest will be easy. Like we can start from the very basic latch, flip-flops, then go to the register, then we can go to the memory. Okay. So synchronous clock sequential will be like this. There is a clock pulses now. Instead of mentioning in the past like as a memory element, and as I said, like memory element can be synchronous or asynchronous. But in case if there is synchronous, which means we need to have a clock pulses, so we can replace this. Yes, we can replace this memory element by flip-flops that's connected to pulses. So this will be as memory elements. Flip-flops, or sometimes we can say all latches. But why we are using flip-flops? Because most likely flip-flops are better than latches, and those are what's used in real life, which is the flip-flops. What's the differences? We will discuss this in this course. So flip-flops and clock pulses, these two are memory elements. Memory elements. Then the timing diagram of clock pulses, again, if you look at the rising edge and the rising edge here, it must be the same as between here to here. It must be between here to here. This is called period or switching cycle. Period or cycle. So there should be cycle. And the clock is depending on what we have. There should be a source of clock. It can be either, like as I said, coming from watch, or you can create your own clock by making a pulse generator that you can do it in the lab. Sometimes we can use the source of the clock based on, there is a device, it's called the quartz, made of quartz. Then it can be a clock source. So there's a small device that we can use it as a clock source, then to create a clock, which is with a different frequencies depending on the flux. Some of them 10 kilohertz, some of them 20, some of them 200, etc. So the clock cycles, we can choose it based on, like there is a hardware device that can be used to generate the clock. Now, how is this device being created? How we can create the clock devices? This is in different course in electrical engineering. It's called digital electronics. So in this course, they are teaching how to create the clock in real life. But now we will assume this device, it's not our scope, we will assume that clock device, we already have it, then we will plug it into our system. Now, how to make the storage elements using latches. So we have like, it's flip-flop circuits, so sometimes some people, they can say like latches are part of flip-flops. But I disagree with this. Even here it's written in the notes. I agree with storage elements can be either latches or flip-flops. So basically, the flip-flops target or the latches target is to maintain, or in other words, we can store the binary states. That's our target, is to store the data. So binary, which is 1 bit, I need to store either 0 or 1. So how can I do? We can use the latches. So, or we can use flip-flops. So basic type of flip-flops are latches. So here in these notes, they are assuming the latches are the basic type of flip-flops, then we can go further. So latches, again, are based on basic circuits. They are very simple to implement, and we can create, from latches, create some other more complicated models. So latches most likely are used more in asynchronous circuits. But in real life, we are not using latches. We are using some updated version of latches, which are called flip-flops. Again, all of this, we will discuss this in next lectures, or today's lecture and the following lectures. So latches, flip-flops. Latches are the basic, flip-flops are updated version of latches, and what we are using in real life, which is are the latches, or are the flip-flops. But latches most likely, as I said, it's most likely used in asynchronous sequential, which is there will be no clock, there will be other type of signal generators. Okay, now how can we create the memory? Our target is to keep the bits stored without any changes. I need to store a certain bits. Let's use an inverter, a small inverter. A small inverter, we need to store the data. So let's assume there is 1. It will store it as, it will be stored as 0. Then 0 will go here as a feedback. It will be 1. So what's happening here? The data will not be stored because sometimes 0, sometimes 1. It will be changed a lot. So this creates something called astable or unstable, which is sometimes 0, sometimes 1, sometimes 0, sometimes 1. This is not acceptable, or this is not, cannot be stored, or does not create our target. So our target is to store the data and keep it hold without being changed. Therefore, we create another inverter, feedback inverter. Then we have here, we can guarantee the output will be stored. Let's assume that the initial output is 1. Here there is a prime inverter, then it will be 0. Then here is 0, it will be 1. So it will keep it 1, it will not change, right? How about if we assume it 0, this will make it 1, then this will make it, it will be 1, keep 1 because it's feedback, then with the inverter will be 0. In this case, we can guarantee it will be stable. Then it will hold this data. Then if we store 0, it will remain 0 forever. If we store 1, it will remain 1 forever. That's the first basic, which is we need to make sure that the information that I'm storing to be kept. It will not be deleted or it will not be erased. So that's how we can store it using 2 inverters. But the disadvantage or the drawback, even though that we can create, it's stable, but we cannot change the states. So okay, we store the data, and this data will be forever. There is no way to change this. Okay, sometimes I need to erase the data. I need to store another data. What should I do? This scenario, it will hold the states as soon as the power is on. If the power is off, it will be reset. It looks like you're creating a small memory. But in these kind of memories, the disadvantage is, again, I need to update this. How can I update it? Then we need to create another version of it so we can update the states. Therefore, we make this approach. This approach, which is a switch, and that switch again can be a transistor, practical one. And the inverters, we already talked about the inverters, how to create the inverters, which is based on the transistors as well. So all of them we can create in our real life. We can create a hardware in real life, these hardware components. You can go to the lab and build these circuits. Okay, what's the advantage of this switch? We add the switch, the status is D. So let's assume the switch is on. Switch, or in other words, like the state D is on. What will happen? When the switch is on here, then here is Q, here is Q bar. Q bar will equal to D, right? Or when the switch is on. Let's forget about this. Yeah, here, D. Then, which is equal to 1, right? How about if the switch, or what will happen to Q? Q will be Q bar, which is 1 inverse, which will be 0. So it will be, if the switch is on, this will be 1, this will be 0, right? Now, if the switch D is off, which is in other words D equals 0, what will happen? Switch is off, the switch status will be here. So let me erase it. Which means the switch is in this position. What's going on? What will happen? It will hold. So what we will see is D will be 0. Therefore, Q will equal to, Q bar will equal to the Q bar here. So it will hold. So Q will be Q bar, which is going to be the same as Q, which is going to be 0. So we can store the data. We can store only the bits number 1. We can store 1. Also store 0, by using this. So by using this simplification, we can use it to store 0. To store the bit 0. By making the switch. If the old status was equal 1, turn on the switch D, then you will store 1. You will store 0. Or if the old status you don't know and you need to store the data, you can use this approach to store the bits 0. There is an implementation that we can make it much easier by doing using NOR gates representation. So we can replace that switch and that's not operator with a NOR gates. So the problem will be easier. How? Here in this scenario, Q bar is the exclusive NOR, which is S plus Q, or here is NOR, using NOR. Therefore, if the switch status S equals 0, or the switch is off, then what's happening? Q bar equals to Q bar, which means hold, no change. Hold or no change. If switch is on, then what's will happen? Q bar will be 1 plus Q all bars. 1 plus any variable will be 1, so it will be 1 bar, which make it 0. Right? That's for Q bar. Then for Q, here, it will be Q bar bar, then it's going to be 0 bar, which is going to be 1. Okay? So we realize that if we use the NOR gates into the bottom and we connect a switch called S, we can use this to store bits 1. Okay? Again, if the switch is on, store bit 1. If the switch is 0, no change. Don't do any change. But how about if we need to store the bit 0? What shall we do? If we need to store the bit 0, we need to replace the switch and the inverter to be what? Into here. Replace this inverter with the switch to be NOR gate, sub inverter. And we can call this R. Then here we can say that Q is equal to R plus Q bar, because this Q bar with NOR, with R, it will be R plus Q bar. So what should we do? If R equals to 0, therefore Q will be 0 plus Q bar all bars. Therefore it will be Q bar bar, which will make it a Q, then it will be hold. If R equals to 1, then Q will be 1 plus Q bar all bars, then 1 plus any variable will be 1 bar, which will make it 0. Right? So in summary, we realize that here is the inverter, here is the other inverter. When we put, here's like switch here and here. If you replace the top switch with R, switch R and NOR gates, and you replace this one with S and NOR gates, switch S and NOR gates, we can create this. Okay? What's the observation that we can see based on this assumption? We can say that when R equals 0, S equals 0, we will remain in hold mode, because that's what we observe here. If R equals 0, we are in hold. If S equals 0, we are in hold, right? If S equal 1, Q will be 1. If R equal 1, Q will be 0, right? So we can say that if R equals 0, S equal 1, then it will be on states. If R equal 1, S equal 0, we will be in off states, which is we will store the bit 0, store the bit 1. Okay? So as a result, we can say this is R, this is S, this is Q, alt, this is Q in U. Or let me write it without Q. I'm sorry, let me write it as Q in U. Then if S equal, R equals 0, S equals 0, we are on hold. If R equal 0, S equal 1, then the output will be 1. If R equal 1, S equal 0, the output will be 0. How about if S equal 1, R equal 1? This is forbidden. It seems that I need to store 1 and store 0 at the same time, which is inconvenient. So this is forbidden state that we don't want this, and we want to avoid this forbidden states. So S, since S will make store 1 and R will store 0, S we will call it sets, R we will call it resets. S from set, R for resets. Therefore, the push button set will store the bit 1, the push button or the button 0 will store the bit 0, or the push button R will store the bit 0. Okay? So and reset, I think you are all familiar with the word reset. Reset like back to the factory, like reset the data, reset the memory, which is clear everything, make everything zeros. That's what this reset. All of this will be zeros. So again, sets store 1, reset will store 0. Whenever set equal 1, this means I already enabled the switch storing 1, then the data will be stored as 1. If you enable the switch 0, the data stored will be 0. So again, this is the implementation. Putting this in memory, then this is called SR latch, because S from resets are S from sets, R from reset. That's why it's called SR latch. Then this SR latch can be redrawn in like nice way using the node NOR implementation, as we see here. This is S, this is R, this is Q bar, this is Q, using NOR gates implementation. And this NOR gates is actually active high. Okay? So when we do like the SR latch, again, it's called SR latch because we have S from sets, R from resets, S for storing 1, R for storing zeros. So in the active high, again, S equal 1, R equal 0, store 1. S equal 0, R equal 1, store 0. S equals 0, R equals 0, hold, which means what was in the past, keep it as is, no change, no change. Then S equal 1, R equal 1, it's not allowed, forbidden. Okay? Now, since we did using NOR gates, can we do it using NAND? Yes, we can do it using NAND. And here when we're doing it, it will be active low, which is the opposites. Because anything active low, it's based on NAND implementation. Anything is active high based on NOR implementation. So active low, it's the opposite. So when S equal 1, R equal 0, we will store 0. When S equal to 0, R equal to 1, it will store 1. When S equals 0, R equals 0, this is forbidden. When S equal 1, R equal 1, this is hold, which is no change. Okay? Any question? So basically, we can realize that SR latch, there are two approaches for it. There is based on NAND, based on NOR. The defaults for SR latch is active high. unless you see some information indication says it's active low. Therefore, you don't need to worry a lot about active low. Just look at active high and that's it. Okay, so again, active high and active low, or SR latch, we can draw it like this way. As a shortcut, if we need to make sure, or to, instead of keep drawing these two, we can make a shortcut by making a box, like this small box. Here is the input S, input R, here is output Q, here is output Q bar. So this box has been created in purpose, so we don't want every time to draw two NAND gates or two NOR gates as we see here. So we need just to make sure that we can do it in fast way. So we denoted this symbol by this box. Two inputs, two outputs. Input SR, outputs Q bar. Sometimes we can draw it like this way. What's the difference between these two formats? You see here, there is a symbol Q. You see here, Q bar, here is a symbol Q. But in order to make a bar, we put a bubble. So just remove the bar into this symbol and put a bubble. This is another approach that we can do. So it's up to you. Either two approaches are fine or two symbols are fine, but keep in mind if you make this, don't mix up with them. So don't, for example, when you draw, use the Q bar, don't put a bubble here. This is incorrect. Or when you remove the bar, keep in mind you need to put a bubble. Okay? Any question? Okay. Now again, let's go in more details about SR latch with NOR gates. Again, when there is a set state, we will store 1. Resets, we will store 0. In set state, S equal 1, R equal 0. Here is S equal 0, R equal 1. And it will undefined states, or we call it when both R and S will equal to 1, which is undefined, or sometimes, as I mentioned it, it's forbidden. Forbidden to get S equal 1, R equal 1. Then, if both of them are zeros, S equals 0, R equals 0, it will hold, which means keep the old value, no change on it. And that's what I want. So sometimes I need to store a specific data. I have all of this data information. I will set a reset or a set switch when I want to store this bit as 1, a reset when I want to store this bit as 0. After store this data, now I want to keep this data, I don't want to erase them. Then I will put all of the switches are zeros. Then it will be S as 0, R 0. This data will be stored without being changed. Then after setting S equals 0, R equals 0, there is no way to change this data. It will be stored. And that's what we want. Okay? So I can change them, or I can control them by changing the status of R, the status of S, by what I used to do. So under normal operation, if the data is stored and I don't want to change the data, they both are zeros. If I need to store, make a set, or to store a bit 1, I will make S equal 1. After that, if I'm done, make it back to 0. If I need to store the bit 0, make R equal 1. That's why it's called set or resets. Set Q equal 1, reset Q equal 0. Okay? So if I need to store 1, make the S1. If I need to store 0, make R 0. Keep in mind, after turning this and storing the data, return it back to its position. Return it back to 0. This is a must, to return it back to 0. So you see here the inputs, S and R, must go back to 0 before any other changes, to avoid indefinite or to avoid the forbidden states. So the latch will go to set states or reset states after make sure that everything is all right. So let's look at sorry. Now let's assume some scenarios. I'm going to assume in the beginning I have a device that S equals 0, R equals 0. In this state, it's in hold. But do I know what's the initial status? If it's not given, then it will be, I don't know. Even though it's hold, but I don't know what it is. Right? So it's on hold. After that, I'm going to say like S equal 1, R equals 0. Then I know that I'm going to store the data as 1. Right? Here's Q. I'm going to store 1. I stored 1. After that, I need to go back to make it 0. Go back, make the switch 0. Then here it will hold, and hold with 1. So you will see that compare between number 1 and number 3. S equals 0, R equals 0, I don't know. Number 3, S equals 0, R equals 0, it's hold 1. Let's assume another scenario. S equals 0, R equal 1, then it will store 0, right? That one we'll call it sets, here this one we'll call it resets. Then let's go back to S equals 0, R equals 0, it's hold. Now I know I'm storing the bit 0. So we can realize something here, make a comparison between like the green arrows. S equals 0, R equals 0, the same as, or like S equals 0, R equals 0, and there's S equals 0, R equals 0, there's S 0, and R equals 0. If it is based on combinational logic circuits, there is no way to get to get different outputs. But here we see that we have different outputs. Even though the same inputs, but I have different outputs. Why? Because the output is not only depending on the present inputs, it's depending on what's in the past. And that's what happens here. This is the idea of sequential logic circuits, which is I can have the same environments, but maybe the testing time is different, then I can have some change. I have the same inputs, but I can get different outputs based on the environment or based on the past inputs, based on the past data. And this here, why the time is matters, that's why the energy storage matters. So we see two different outputs with the same inputs, again, depending on the past. So we can store 1, store 0, depending on the conditions. So here is like a truth table. This is Q bar. If S equal 1, R equals 0, then we will store the bit 1 for Q. Q bar will be 0, of course, because Q bar is the opposite of Q. Then here we are in set mode. Then if we both are zeros, we are on hold. So it will be Q will be 1, R Q bar will be 0 because in hold. We'll keep the old states. Then 0 and 1 we will be in resets because R equal to 1. Then Q will be 0, Q bar will be 1. After that, both are zeros, so we are on hold. Then if both are ones, this is forbidden states, which is we don't want this to occur. Avoid this, or will be something wrong happening. Okay? Any question? Okay, I'm gonna draw this timing table, so you will see this a lot also in this course. I'm gonna assume this is the timing table of S, this is the timing table of R, this is the timetable of Q. So I'm gonna assume this is the switching sequence. Here is S, R, here is S. And I'm gonna assume R like this. Okay. And your target is to find Q. How can we find Q? The first observation, try to separate or isolate the changes. This is the first step that's as a must every time when you do the timing table. Locate where are the changes and make a guidelines on it. So there are some change here, right? And there is another change here, right? There is another change here. change here. There is change here. Change here. Change here. And change here. Okay? Then try to put values on each one. So the value of this one, for example, this is 0, 0, here is 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. Okay? Now, after assigning the values, we can know what's going on here. We can know the first status here, it's in hold. Here is in sits. Here is hold. Here is resets. Here is hold. Here is sits. Here is hold. Here is resets. Here is hold, right? Then now we can draw the timing later on. How? The first point, it's on hold. Now look at the initial condition. Look at, for example, the question or the problem. Is the initial condition given? If yes, keep it as the initial condition. Let's assume, like, if, for example, the question says the initial condition is 1, then put 1 and keep going. But here, the initial condition is not given. So what's gonna do? We will put like this, keep it fuzzy, and so I'm gonna write like I don't know or don't know. We don't know what is this. So when you don't know, I used to prefer to do it like this way. Now the next cycle, S will be 1, which means it will be sits. So we know that it will be 1, Q will be 1 because we are in sit mode. Now the next cycle, 0, 0s, we are on hold. Hold means keep the old one. Now the next cycle, 0, 1, which will be resets. So it will be 0, right? Then here, hold, keep hold. Now we have sits, make it 1. Then hold, make it hold. Then reset, make it 0. Then hold, hold. And that's properly done. So whenever we deal with timing table, the first step, look at the changes, make a guidelines for the changes. The second step, put zeros and ones values. Then third step, make it determine the mode, hold, set, reset. After that, you can draw. Then it will be much easier. Okay. Any question? How about the other type of SR latch, which is with NAND gates? How can we deal with this problem? With NAND gates, deal with this as active low. So whenever S equal 1, R equals 0, we are on resets mode, which is Q will be 0. When S will be 0, R will be 1, we are in set mode, which is Q will be 1. When S equal 1, R equal 1, we are on hold, while S equals 0, R equals 0 is forbidden. This is the opposite of what we know in the active high, right? Just the opposite, replace 1 by 0. And that's it. So all of this is just like the same way that I mentioned. Then that's how it looks like, the SR latch with NAND gates. So when S equal 1, we will be in resets. Oops, here is resets. Or actually, let's look at the zeros. Because of this 0, we are in resets. Because here is hold. Because S is 0, we are in sets. Here is hold, this is forbidden. Or undetermined or indefinite, no matter what it is. So, like this status that we don't prefer or we don't want. So active low is the opposites of what we used to deal with. Okay, now I'm gonna assume also a scenario with active low, a timing that table like this. Here is S. Here is R. Okay. Now we need to find the Q and assume an active low. So the first step, as I mentioned earlier, look at the guidelines. Then let's do locate or put the values. Here is 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1. Okay? Then determine the states. Here is, remember, it's active low. Therefore, here will be hold. Here will be sets. Whenever you see the 0, it's not the 1, no, it's this. Here there is hold. There is resets. Here is hold. Here is sets. Here is hold. Here is resets. Here is hold. Okay, does this make sense? Now, do we have any information about the initial condition? No. Then we say, I don't know. Okay. Then after that, we are in sets. Then hold, resets, hold, sets, hold, resets, hold. That's it. Clear? Any question? So you see now, dealing with timing diagram, if you understand it very well, it will be very easy. So make sure to understand the basics. Then now, later in this course, we'll be in more complicated analysis, more and more and more. So if you don't understand the basics, don't worry what will happen later. It will be much easier. But keep in mind to be up to date and understand step by step, understand the procedures. Now, there is a modification on SL latch by adding a control units or adding enabling button or sometimes gates. So here sometimes we call it EN, sometimes we can call it G, EN or G. What's the reason we need to add enable button? Sometimes I need to look this data, so this data will not be changed no matter what's S or no matter what's R. I need this data to be stored, and I don't want to make any effect on it. So I'm going to make enable button. If the enable is off, there is no way to update the data, no matter if it's S is 1 or R is 1. Because we have the hold status when S equals 0, R equals 0, we have the hold status. Yes, that's fine. But how about if I need to add enable? So this enable button. I'm sorry, I have allergies. Okay, so when S equal 1, S equals 0, R equals 0, we are on hold, which is no change, that's fine. But I need to add another enable, so no matter what are the switches of R or S, there will be no effects. That's why we add enable button. And by looking at the truth table, when enable button is 0, there will be no change, no matter what's the value of S, no matter what's the value of R. That's why we add X or don't care. Don't care about the value of S, don't care about the value of R. All of them will be zeros. I'm sorry, the output will be hold based on all status, no matter what R is. So we can create an enable button to enable the system. When enable is on, is 1, we can apply the normal SR latch that we know earlier. Apply the as we know in the past. So Q equal 1 for resets. For sets equal Q equal 1, for reset Q equals 0, then there is forbidden states. And that's how actually looks like. We added a new, for example, gates here. Then this gates will be connected to enable no matter if it's active high or active low, but let's assume the default is active high, even though that there are NAND gates. NAND gates means active low, AND gates active high, but here I'm dealing with active high. So let's assume active high. Okay? So here, in this scenario, we will make sure, or we can guarantee that by adding the enables button, sometimes we call it gates, no matter if you call it E, N, or G, this means this button or has been added to enable the system or disable it. So this is how we draw this scenario. We just add a new one called gate here. And we can either by making Q bar or put the bubble, as we know, this is, we already are familiar with this, but the difference is we have a gate, and that gate will determine what the output will be, or depending on the gates. So let's assume this scenario. Here is the clock. Then there will be S and R. Most likely, sometimes enable button can be connected to EN or to the gates to the clock. Let's assume for some reason we connected the enable to the clock. So what shall we do? Let's assume S is given as this way. Okay. And I'm going to assume R as this way. Come on. So our target is to find Q. So how can we find Q? Let me see something, make sure that I have the right waveform nodes. No, we like. Okay. So now, first step, make the guidelines. So, we need to be careful when we do the guidelines. Okay. Now, let's do the put the values. Here is 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0. 1, 0, 0. 1, 0, 1. 1, 0, 0. 0, 0, 0. 0, 1, 0. 1, 1, 0. 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay? You need to keep in mind something, which is when gates or the enable equal to 0, don't care about S and R. It will be holds. When E or enable will be 1, then it is SR probably. Okay? So the first observation before looking at S or R, look at E. If it is 1, then okay, look at SR. If it is 0, then hold without looking at S and R. So let's look at this scenario here. So enable is 0, then we are on hold, right? Here, hold, because enable is 0. Here, enable is 1, then look S and R. S is 0, R in 0, then we are in what? Hold, right? Here is the first hold because enable 0. Here is hold because SR, both are zeros. The second one, S equal 1, then we are in sets. Right? The next, enable is 0. Then we are on hold. Right? So let me draw it step by step so to make sure we are up to date. So the first one, we are on hold. But do I have the initial condition? If yes, put the initial condition. If no, you will say I don't know. How about this? The second step, it's on hold. Do I know the initial condition? No, it's still. So that's why for the first two, I don't know. Okay, do you agree with me? Then here we are in sets, so it will be 1. Then here we are on hold, then it will remain at 1. Okay? So this will be 1, hold will be 1. The next step, enable is 0. Right? So we will still be on hold because the enable is 0. Okay, you agree? So it will be on hold, remain again. Now here enable is 1. Enable is 1, look, is there any updates? S equals 0, R equals 0. Therefore, we're still on hold, right? Okay, the next one. Here S equals 0, R equals 1. What does this mean? Resets, right? Because S equals 0, R equal 1, and enable equal 1. So we are in resets. Then here, enable still 1, then look at 0, 0, we are on hold, therefore it will remain 0, right? Then after that, the enable is 0, then the whole period enable is 0, these two periods, because it's 0, then it will remain zeros, right? Without looking what's inside in S and R. Then you will see here, clock become 1, then look here at S equal 1, then it will go to sets. So you see something maybe kind of weird. There's an update happening here, but it will not be reflected here. Why? Because the enable button was off. So even though the enable button was off and the switch was on, didn't do the updates. Okay? So let me erase this. Now, the next step, 0, 1, 0. So whenever the enable is 0, this one and this one, this makes it hold, because the enable is 0. So for the whole period, it will be 0. So it's hold. It will remain on hold. Then here, enable is 1. Look at the status. Here is 0, 0. This means hold, right? So it will hold. Now, there is enable button, 0. This means hold. So here is hold, here is hold. It will hold. Then here, the enable button is on. Therefore, here is 0, 0. Then it will be another hold. Then it will be like this. After that, this is 0, means hold. Then like this. Okay? So that's how we draw it. So you need to be aware how to do these timing diagrams, no matter how it looks like, how tricky it is. Any question? Yeah, by the way, there will be, as you know, the quiz on Friday. The quiz will not cover today's lecture. So the quiz will be on combinational logic circuits. So don't worry about the quiz for today's lecture. Study on all of the combinational logic circuits, because it's going to be a design problem. Like a real life design problem. Design something, a program to create something. So you need to convert the verbals into, or the written into a certain truth table. Then you can do kernel maps, whatever, or to make the plot, or to make the logic circuits. Then you can convert this to NAND gates or NOR gates if it's required. Okay? This is going to be like as a cumulative example, because it's called combinational logic circuit, while today's lecture is not included into that quiz. Now, in SR latch with enable, before starting, any questions about this example? Okay, SR latch, here is S, here is R, here is gate or enable, here is Q, here is Q bar with bubble. So we can say that in SR latch, there is one switch for sets, one switch for resets, and there is two hold states, which is when gates equal 0, we are on hold, or when S and R both are zeros, right? So we can realize that there are some, or we can think, can we simplify it more? Which is, since we have two on-hold states, how about if we make it one? Can we make it one? How about we have two switches? Can we make it one switch? The answer is yes. So the question here, can we replace two switches into one and replace two hold to one, such that if the switch is on, we will make it sets. If the switch is off, it will be resets. If the gates is on, then stored data. If the gate is off, it will be hold. So, as a result, we don't need to look at, to make two switches, S and R. We can create one switch. If the switch is on or off. On, store 1, off is 0. By looking at enable. If enable is off, then hold. So we can get 3 instead of having 6 possibilities, or we can have only 1 or 3. On, off, hold. That's it. Then, and also, we can avoid the forbidden states, which is, in the forbidden state, S equal 1, R equal 1, we can avoid this. So this can be a great benefit And that switch, we can call it D, like D equal 1, D equals 0. That's what we call it D. Therefore, we can replace this by call D latch. So the D latch idea is basically converting these two switches into one. And avoid the forbidden state, avoid the two on-hold states. So we can have, the life will be much easier by using this. Therefore, the truth table will look like this. If the enable or the gates, no matter if it's called G or EN, if it is 0, then no change, no matter what's the switch status D. So it will be on hold. We are on hold. And that's what we know in the past. If the enable is on, look at D. If D is 0, it will be reset. If D is 1, it will be set. So we can store the data in an easier way than SR latch, right? That's the benefits of using D latch. If we need to draw this, it can be like this way. So we have D and G. We can avoid S and R. And again, another advantage of it, we are for avoiding the forbidden states. We can remove S and R, so we are reducing the complexity, removing the forbidden states, and maybe reducing some costs, because I'm not using two switches, I'm using one. Then the timing or the diagram can be either this way or Q, and sometimes we can call it Q bar without bubble if you put the Q bar. So either ways are fine. Any question? Let's look at the following timing diagram and see how we can do the analysis of it. Imagine this is D and this is gates. We need to find the Q. I don't know the initial condition. What should I do? The first step, draw the guidelines. This is very essential for you. Draw the guidelines and you can determine what's the current status or the next status. So the guidelines, here is a change. Make it more clear. Oh, I forget this. Keep in mind here, if G equals 0, then hold. If G equal 1, then G will be the same as D. If D is 0 or 1, we'll copy the waveform of D. Then look at the first step. Let's put the values. Here is 0, 0, 1, 0, 1, 1, 1, 1, 0, 1. Here's still 0, 0, 1. Oh, I forget also to put this guideline. One, here is 0, 1, 1, 0, 1, 0, 0, and there's a guideline here. 1, 0, 1, 1, 0, 1, 1, 1, 0, 1. Okay. Now, let's plot the waveform. The first step, G equals 0, this means we are on hold. And we don't know what it is, what's the first step. So let's keep it on hold because we don't know what it is, right? Now the second one, G is still 0, then we are still on hold as well. These two are on holds because, again, we don't know what's the initial condition. And again, G is 0. So it will not detect what's happening when G is 0. So here you see D was 1, then back to 0, and there is still G was 0, then it will not detect what's happening in the toggle here, or the change that happened here. It will not be detected. So this here, 1 and 1. 1 and 1, the first step, look at gate. If gate is 1, then copy the waveform. So during this period, these 3 periods, gate is 1. So what I'm going to do, I'm going to copy the waveform of D. When gate equal 1, copy the waveform of D. So the waveform of D here is 1. I'm sorry, the waveform of D was 0. Then there's a small pulse, 1. Then it will back to 0 until reaching this edge. Now we reach the edge of this edge. Okay, let me copy it again. Here, copy it. Then here. Then in this scenario, G will be 0. Therefore, it will be on hold. On hold, what's the status? 0. Keep it 0. No matter if there is any changes at D, don't look at D. It will be on hold. Okay? Now in this status, G equal to 1. Then copy the waveform of D. And here D equal 1. Then we will copy the waveform. So we will copy this. So we will copy this. It will go to 1. Then it will go to 0. Here. Now here in this scenario, G equals 0, then it will be on hold. G equals 0, it will be on hold. So for the total period, it will be on hold. Since it is 0, it will remain zeros. Then here in this scenario, G will be 1. G will be 1, then copy the waveform. What's the waveform of D is this. So copy this. Copy the waveform. And that's it. Okay? Any question about this? Okay, that's it for today's lecture. Next lecture, we're going to continue on more about this. So we will stop here. Thank you.